Okay, so chapter 4, we are getting into moles, the little blind animals that crawl under the ground. No, not those types of moles. But I do have our class mascot, Professor Molarity, that I brought out for our first exam, based on the name. Okay, so let's say that you're ordering donuts. Donuts are great if you just want to grab and go breakfast. If you've got an office meeting or a seminar, a lot of church groups will also have donuts often in the morning. Usually if you're ordering donuts, you're probably ordering 1 or 2 boxes, probably less than 1 or 2 boxes. Maybe you're just getting a half dozen donuts for your family, or you just eat half a dozen donuts every morning. That's a choice. However, let's say that you're hosting a large morning party. Maybe Mima is having her 80th birthday and you're having everyone over and you want to have donuts because she gets sleepy in the afternoons and the evenings, and so you want her to be at her best. So let's say you're picking up 250 donuts. Mima's got a lot of friends. If you were rolling up to the donut shop and you're like, hey, let me see the 250 donuts, they're already going to have them boxed up for you. And if you wanted to open up all the boxes and individually count up to 250 donuts, that would be quite a task. It would be a lot easier if you could just count the number of boxes. So that's probably what you do. You'd count up how many boxes do we have, does that add up to the correct amount? So let's say that we're doing that. We're picking up an order of 250 donuts, not boxes, 250 donuts from the bakery. How many boxes of donuts would we expect to be in our order? We would need to know how many donuts fit in a box. Assuming that they're these regular round donuts, how many fit in a box? 12. So 12 donuts equals 1 box, or a dozen donuts, not a baker's dozen, a dozen donuts. 12 donuts, 1 box. So if we've got 250 donuts, and we can get 12 donuts in 1 box, that's a conversion factor. So 1 box equals 12 donuts. So we would take 250 and divide it by 12, and we would get 20 with a remainder of 10, because I don't know what 10 divided by 12 is off the top of my head. Boxes. They're probably not going to just set 10 donuts out by themselves. They would probably also be in a box. So we would expect 21 boxes of donuts. So we could roll up to the bakery and count the number of boxes. Are there at least 21 boxes? If so, yeah, that's probably right. We'll go ahead and pay for our donut order, get some help loading those into our car, and Mima is going to have a fantabulous 80th birthday party with all of her 249 friends. Much faster than opening the boxes individually to count every single individual donut. A dozen or 1 box is a real convenient number for donuts, because donuts are relatively big. If we are counting up numbers of atoms, however, a dozen doesn't even approach getting anywhere close to having a reasonable number because atoms are so small. I think we've talked a little bit about how small atoms are. I think it's something like 1 million atoms lined up side by side, like touching distance, just as close as they could possibly be, gets across the width of 1 hair. And I think it's something like 11 million to get across, or maybe it's more than that, to get across like the width of your pinky finger. So dozens aren't going to cut it. We need a much bigger number. And our version of the dozen is the mole, M-O-L-E. And to shorten that, we drop the E. So this is the shortened form. So typically we will just write MOL. It means mole. It has to be MOL because M means something else, depending on the context. And 1 mole equals this really big number, 6.022 times 10 to the 23rd power. This number is called Avogadro's number. It's named after Amedeo Avogadro, who came up with the idea for the number, but other people later on in history figured out what the number is. You can also find versions that have more decimal places if you need them online, but 6.022 times 10 to the 23 is a good start. This is a number that I would recommend having memorized. Avogadro's number is sometimes also written capital N with a subscript of capital A after it. And this is part of the reason that we learn scientific notation. Because writing 6.022 times 10 to the 23 is a lot faster than writing this. It's also a lot less confusing because I'm not even sure if I wrote the correct number of zeros. And if we wanted to add in commas, it would look something like this. And I think I did screw up because I think it's supposed to be 602 sextillion. So I think there's supposed to be another zero in there. My bad, my oopsie. So using scientific notation saves us writing out all those zeros, and your calculator also just is not going to let you write in that many zeros most of the time. So the way that we use 1 mole is that we convert between 1 mole and atoms or formula units or molecules, just depending on what the context is. The basic idea is it's the Avogadro's number, 6.022 times 10 to the 23, of whatever the smallest unit is. So let's say that we want to convert 9.5 times 10 to the 25 atoms to moles. We're going to start with our 9.5 times 10 to the 25 atoms. And the conversion factor is 1 mole equals Avogadro's number of atoms. So we're going to divide by Avogadro's number. That part goes on the bottom. And 1 mole goes on the top. And this should leave us with a slightly less ridiculous or significantly less ridiculous number. If you have your calculator with you, please put this into your calculator. You should end up with a not very ridiculous number, something that you could imagine. So 9.5 times 10 to the 25 divided by Avogadro's number. You should get something like this. And if we care about sig figs, optional in this case, I don't really care for this question, but it would be about 160. Have I talked about the dolphin noise key on your calculator? Has that been mentioned? Okay, so there's a key on your calculator that's the dolphin noise. Not all calculators will necessarily have it. What noise does a dolphin make? Right? It's a lot of E's in a row. So there's a key on your calculator, good, that's 2 capital E's next to each other, the EE key. Find it if you have it. What this does is that it puts in a small capital E. The small capital E is not the same as the lowercase e. They're not the same. So what the small capital E does is it tells your calculator times 10 raised to the power of whatever follows this. This is what it tells your calculator. So for example, if I wanted to put this into my calculator, I will typically put in 9.5, small capital E, hit the dolphin noise key, 25. And then I'm going to divide by the Avogadro's number. So calculator puts in this / 6.022, hit the dolphin noise key, take out the small capital E, 23 equals. That will give you the correct answer. You can also use the times 10 to the power of key to enter in 10 to the 23 and 10 to the 25. If you do this, you need parentheses on the bottom, because your calculator will not necessarily distinguish, especially if you put a multiply, it will not necessarily distinguish that these two numbers are linked. This small capital E tells your calculator these two things are linked together, don't separate them. So make sure that you have at least one way of putting this into your calculator and getting the correct answer. It should look something like 158 moles. Questions? I do that dolphin noise bit almost every semester for every class that we talk about moles. It's awesome. It's always a hit. All right, the element carbon exists in a couple of forms. It exists as graphite, it exists as diamond. How many moles of carbon atoms is 4.72 times 10 to the 24 atoms of carbon? What is our given information? What's some information that we can use to solve this problem? It's the number that we're given. 4.72 times 10 to the 24 atoms of carbon. What are we finding? We are finding moles of carbon atoms. It's right next to our question word. How many? So we're finding moles of carbon starting from atoms of carbon. So atoms C going to moles C. We can do this in one step thanks to our Spanish lawyer's help. We're using his number. So using our 4.72 to start times 10 to the 24 atoms C. Who remembers what Avogadro's number is? How many avocados do we have? Unlimited avocados. No, not unlimited avocados. It's 6.022 times 10 to the 23 units. In this case, our units is atoms, and that's the number that's in 1 mole. We are starting with atoms going to moles, so we're going to divide by our Avogadro's number. And the atoms part goes down there too. Atoms cancels, and the 1 mole part goes on top, and we would be left with moles carbon. Into our calculator, 4.72, dolphin noise key, 24, divide by 6.022, dolphin noise key, 23. We end up with 7.84, after rounding, moles of carbon. Questions? Cool. Let's say that we want to know how many hydrogen atoms are in 2 water molecules. Water has the formula H2O. The 2 here, meaning that we've got 2 hydrogens in every H2O. So we can figure out how many hydrogen atoms we have, because we've got 2 hydrogens in 1 H2O. That's a conversion factor. So starting with our 2 H2O, there's 2 hydrogens in each of those. So we've got 4 hydrogen atoms, and we can also just count that up, right? These white dots, these white orbs, those are our hydrogen atoms. We've got 2 water molecules, we've got 4 hydrogen atoms. This is a calculation that we'll do several times. Not this exact one, but this idea of counting up how many individual parts do we have. Let's say that we've got a lot more water molecules. We've got 1.5 moles of water molecules, and we want to know how many hydrogen atoms we have in that many moles of water molecules. We know that water has the formula H2O. So 1 H2O, if we were to hit it with our little atom smashing hammer, we would get out 2 hydrogens. That's a conversion factor. So we could start with 1.5 moles of H2O. We would need to convert to molecules to figure out how many individual H2Os we have. So we multiply by Avogadro's number, because that's the number of molecules that's in 1 mole. So this first part, gets us the number of molecules of H2O. Then figure out with our little atom smashing hammer how many hydrogens do we get out. It's 2 hydrogens for every 1 H2O. So we would get out this absurdly large number of atoms of hydrogen. Questions? The other reason that we want to be able to know or figure out how many of each individual part we have is to calculate molar mass, which is something that we will do quite a bit in the class. So the molar mass is the mass of a mole. Mass of 1 mole of whatever the substance is. Conveniently for us, this is numerically equivalent to the atomic mass in grams. So on our periodic table, if you find an element, you look at the number below the element, that's the atomic mass in atomic mass units. Very aptly named. The atomic mass unit number is the same as the grams per mole. So carbon, for example, on the periodic table, the one that we've got in class, the box looks something like this. This number down here is the atomic mass. If we're using units of AMUs, it's the exact same number as the molar mass. So if we've got 1 mole of carbon atoms, that's the number of grams that's in 1 mole. Super cool, very helpful. We can find them all on our periodic table. You never have to have your molar masses memorized. That doesn't mean that it won't help. Some of them you will inadvertently memorize, but I'm not going to force you to have them memorized because it's a waste of time. If we're calculating molar mass, it's kind of like counting up cash. If you're working a cash register, or if you're buying something and you're paying in cash and you have exact coinage, it's similar to counting up, okay, well, the penny's worth 1 cent, the nickel's worth 5, the dime's worth 10, the quarter's worth 25. So count up each of the individual coins. How many of the coins do I have? Right, multiply the value of times the number of coins, add all of this up, and that's the amount of the coins. Same with dollars and whatever else. Molar mass is a similar thing. It's just a little more complicated because our molar masses aren't as nice and round and even. So what we're going to do, each of our elements is going to have a molar mass. So we're going to pick out what elements do we have. So for Na2CO3, sodium carbonate, we've got sodium, we've got carbon, we've got oxygen. How many of each do we have? We've got 2 sodiums because of the subscript of 2. We've got 1 carbon because of the invisible 1. We've got 3 oxygens because of the subscript of 3. Then we go to our periodic table, either the one that's up on the board, or we look at the one that's on our yellow sheet that I would normally have right here, or the one that's in our wallet. My wallet's in the office. And we would find the molar masses from wherever we get our molar masses from. We'd write those up, we multiply the number of atoms times the molar mass to get the total for that element, add them all up, that's the total. feels like it might be a long process. Once you start to get the hang of this, it does go by pretty quick. And the other nice thing is you don't have to use any parentheses to do this on your calculator. So let's say that we want to calculate a molar mass of calcium nitrate. This will be our last slide. Calcium nitrate's used in fertilizer. We want to figure out the molar mass of calcium nitrate. So we want to break down what elements do we've got. We've got calcium, we've got nitrogen, we've got oxygen. How many calciums do we have? We've got 1 calcium. There's no subscript after calcium, so we've got 1. How many nitrogens do we have? We have 2 nitrogens because we've got 1 in NO3, but we've got 2 of them. So this 2 multiplies across to the numbers that are inside. So we've got 2 nitrogens. And we've got 3 oxygens per nitrate. We've got 2 nitrates, so 2 times 3. We've got 6 oxygens. Then we would go look up what are our molar masses for these. Calcium is about 40.08 grams per mole. Nitrogen, 14.007 grams per mole. Oxygen, just shy of 16 grams per mole. So we get our little subtotals. I don't feel like doing 6 times that in my head. 95.994 grams per mole. If you have a calculator that can do multiple things at once, you don't have to add them up individually. You don't have to multiply them individually. You can do them all at once. And then we add all of those together. And we get 164.088 grams per mole. How many significant figures? Dreadful question, awful question, bad question. Mr. K, don't ask us that question. It would be 5. So we can do significant figures for these questions. In this case, it's based on this 40.08, so we have to do it for the multiplication first. We don't change any place values when we do the 6 times 15.999, so this retains its 5. This stays as 5. The 40.08 is 4. Then we're adding them all together, and so 2 decimal places, and that's how we end up with 2 decimal places in here. The secret, a little secret for you. You almost never have to worry about the significant figures of your molar masses as long as you use enough decimal places. So if you're using the numbers on your yellow sheet, for example, you should always have enough decimal places that we don't worry about it, because it's not going to limit our significant figures for our calculations. Even in this case, we used the 40.8 from the periodic table in the class. We still have 5 significant figures. More often than not, that's not going to be a limitation, so we don't need to do significant figures calculations for molar masses. Praise hands emoji. Any questions? Great.